Hello, everyone. For the next 15 minutes, we are going to talk about ozonation and how we implement ozone in saltwater RAS facilities. So a few things about us. Oxyguard Group consists of Oxyguard International, Cobalia, and Water APS. Oxyguard is a leading company manufacturing control and monitor equipment for aquaculture. Cobalia is our aquaculture management software, and Water is a manufacturing company of ozone. The water in low exchange RAS is heavily loaded by organic and inorganic compounds, where dissolved organic matter, particles, ammonia, and different micropollutants are accumulating. These compounds originate mainly from the fish feed and fish excretion. As water circulates, these compounds accumulate, and they are food for many pathogens and other bacteria. Ozone is a good candidate in aquaculture to improve the overall water quality. It's a very strong oxidating agent, reacting rapidly with non-biodegradable and degradable organic matter. In presence of ozone, the protein degradation is enhanced, the water clarity, UV transparency, and the processes of filtration, nitrification, and coagulation are improved. Ozone is also a very good disinfectant, able to kill virus, parasites, and bacteria. A very good characteristic of ozone is the hydroxy radicals. When ozone decomposes, hydroxy radicals are formed, which are the strongest oxidant that you can find. They are highly reactive, non-selective, and they can react with compounds that the ozone alone can't deal with, like geosmin and some other resistant compounds. Ozone in RAS has a lot of benefits. It improves the overall water quality, which is crucial in such systems in order to support growth, minimize the disease outbreaks, and improve the overall fish welfare of the fish. Ozone chemistry in salt water is much more complicated due to the presence of ions, and especially bromide. Bromide reacts rapidly with ozone, and then some compounds like bromide and bromate are formed that they are very, very toxic. Ipobromous acid and the dissociated form ipobromide, they have very long lifetime, and therefore they are very important because during this long lifetime, a lot of reactions can occur. Ipobromide reacts with proteins and ammonia and creates bromamine, which is very, very toxic for fish and the other aquatic animals. We have to keep in mind that when we ozonate saltwater systems, we do it in order to improve the water quality and not to disinfect, because in order to disinfect, we need much higher ozone dosages, and that means that the risk of creating all these brominated byproducts increase significantly. So far, there are some approaches in order to deal with these byproducts, like using activated carbon or UV filters, or sucking it out of your system, with benefits and disadvantages, but that's a story for another time. Although ozone has a lot of benefits, it also has some challenges. The risk of losing fish due to overdose, or when you have excess of ozone, even in very low concentrations, can be harmful for the fish and also the byproducts that I just mentioned. So the risk of losing fish, the failure to monitor, and the cost are some limiting parameters, making the aquaculture managers reluctant to use ozone. In Oxyguard, we have the whole package. We have our own ozone generator, we have ozone sensors, and we have control unit, so we can do the ozonation safely and efficiently. Now I will present to you some results from a project called RAS. It took place in Denmark. We just finished with it. It was funded by Fiskery Styrelse and EU. And the whole project was about ozonating safely and efficiently saltwater RAS. The main thing in this project, like it was kind of stepwise, so the first thing it was to develop analytical methods so we are able to identify the hypobromus acid. We had to know what we are measuring. So we did a lot of laboratory experiments and we made a very efficient analytical method. And then we collected water samples for a commercial saltwater RAS facility in Denmark. And these water samples, we subjected them to different ozone dosages, as you can see here. What I did? Where is the laser? Okay, I don't know where is the laser. So we back here. So we applied different dosages, like 10 milligram per liter, 5, 2, and 1. And we can see that when we applied the ozone dosages, the high ozone dosages induced rapidly the formation of hypobromus acid. When we applied 2 milligram per liter, we had a slight formation of brom, while in the 1 milligram per liter, we had no formation of hypobromus acid. In all the cases, we had no residual of ozone. It's very important to say that the level of the organic matter that is present and the character play a very big role in the potential formation of hypobromus acid, because the ozone, let's say, is lazy. It will react first with the easy compounds, that is usually whatever has carbon, and when the carbon is gone, it will start reacting with whatever is left, and in that case, brom, and then it will start making the byproducts. So because for us organic matter is important, we wanted to take a deeper look of what it is inside the organic matter. So we use fluorescent excitation matrix spectroscopy and paraffin analysis in order to identify the different components that they are inside the organic matter. This analysis revealed 4 components, 2 humic, 1 biological, and 1 protein-like. So these components, we expose them to different ozone dosages in order to see the reactivity, which one is the easiest to remove. And it was found that the protein-like, so the blue line, it was the one that it was the most reactive with ozone. Then we wanted to see if there is any correlation between the 4 components of organic matter and the production of hypobromus acid. And here we see that as the components of the organic matter decrease, the formation, the black line of hypobromus acid increases. According to literature, 2 milligram per liter of ozone is the dose that the hypobromus acid starts to be formed, and this graph confirms that. Then we wanted to see what is the maximum safe ozone dose for this specific system, and to do that, we correlated directly with the hypobromus concentration and the TRO threshold, which according to literature is 20 ppb. Above 20 ppb, the welfare of the fish is compromised. And in this graph here, we can see that the 1.2 milligram per liter is the right ozone dosage for this system in order not to make any hypobromus acid. Then we went on site and we wanted to verify if the UV is a technology that we can use in order to destroy all this hypobromus acid that might be formed in the RAS. So what we did, we put UV there, and in order to remove 1 milligram of hypobromus acid, and to remove 90% of that, we needed 1.5 kilowatt per cubic meter. And to remove 99% of this 1 milligram per liter of hypobromus acid, we needed double this amount, so 3 kilowatt per cubic meter. This amount is huge if you consider that we are talking about a side stream experiment. So in a big RAS facility with all this water that has to be treated, and with the UVT that is much, much lower than what we use in the side stream, you need a huge UV system, and it's very expensive. So the UV is not a solution, and the most obvious solution is never to make this hypobromus acid because it's very difficult to get rid of. Here is an overview of the system that we had up there. So untreated water entered an oxygen cone that was the reaction chamber, and ozone was coming in. Then we have some oxygen and an ozone sensor, which was linked to our control unit, and we were readjusting the ozone dose. How to dissolve ozone is something very, very important because ozone is expensive to produce, not because you need equipment, but because you need energy to produce ozone. So in order to, for each gram of ozone produced, we have to make sure that we transfer all of it into the water. So ozone solubility is very important. In this project, we tried 3 different technologies, the oxygen cone, skimmer, and vacuum air lift, and we tried to compare which is the most efficient to dissolve ozone. We applied 4 different ozone dosages, and all these 3 equipments were placed before and after the drum filters in order to see if the positioning affects the treatment. Our results suggest that all 3 technologies were efficient, and there are some potential gains of placing them after the drum filters. Just to sum up, this experiment happened as a single-pass experiment, so much more benefits would happen if we had done it in full scale, and that's our next step. This project confirms that we can safely ozonate saltwater facilities without forming hypobromus acid, and we can apply ozone dosages much higher than those applied in the industry because of the fear of ozone and the byproducts. You are welcome to visit us in our booths. We have 2 booths to talk more about ozone.
Thank you very much, Aikaterini. I think we have time for 1 short question, if anyone has any questions. If not, I think we have 1 question for you.
How do you see this new technology impacting operational costs in saltwater RAS?
Ozone is expensive, but is also very efficient. I believe that the potential of ozone is huge. The benefits are many, but now also in the exhibition outside, I see that people are very, very interested, and they are not as skeptical as they used to be. So I think that there is great potential.
Thank you.
Thank you very much.
Bye.
1 last applause.